Welcome to Calculus. Today we will investigate differentiating quotients, focusing on using the rule for different types of functions. Let's take a look at three examples. So our first example is with a numerator and a denominator that are both polynomials. So we see here for numerator I have 2x cubed plus 5, and the denominator 4x to the power of 5 plus 2. So if I want to differentiate the whole function y, I need a rule that will accommodate this fraction setup. So I want to bring the quotient rule. So let's write it first, and then what we'll do is we'll apply it to this particular function. So what the quotient rule says is if I have a function, we'll call it big F of x, that's made up of the division of a smaller function, so small f of x divided by, for instance, g of x, then the derivative of big F of x has this pattern. So it again is a fraction itself, and it's the difference of two products. So the first product is g of x, just the original function, times the derivative of f of x, and then we're going to subtract, and we'll do a switch. F of x times derivative of g of x. So that's what I've got in my numerator, and it looks kind of like our product rule, except notice there it's subtraction. In my denominator, I have g of x squared. So that's my rule, and what I want to do is apply it to this particular function here from example number 4. So what I want to do first is just find my parts. I have basically four things. I've got g of x's, I've got g derivatives, I've also got f of x's, and derivatives of f of x. So basically four items. So I need to start off by saying, okay, what's my f of x? So I notice in the rule it's in my numerator. So that means for me, my f of x is going to be this numerator 2x cubed plus 5. I'll go ahead and identify my denominator. My denominator in the rule is g of x. So in this particular example, I'm just going to call whatever's in the lower part of that fraction g of x. So then I notice that I need the derivative of each of those, f of x and g of x, in order to substitute into my rule. So I'll take the derivative of f of x, and notice we do this separately for each part. So I'm going to take 2x cubed plus 5, take the derivative of that polynomial. So remember the constant coefficient rule just stays out front, so that 2 just stays there. And then the simple power rule says take the derivative of x to the power of 3, bring the 3 down as a coefficient, x to the power of 3 minus 1. So we'll simplify that, but let's take the derivative of plus 5. That's a constant. Derivative of a constant is going to be 0. So my derivative of that numerator, which I'm calling f of x, is going to be 6x squared. I also need to take the derivative of the denominator. So the derivative of g of x will be similar to what we just did with the derivative of f of x. So g of x again is 4x to the 5th plus 2. So I'm going to apply my constant coefficient rule. 4 just stays. The simple power rule brings down the old power as a coefficient, x to the power of 5 less 1. And the derivative of 2, a constant, is 0. So the way that'll simplify for derivative of g of x is 20x to the power of 4. So then I've got my four parts, and at this point I'm ready to substitute them into the quotient rule. So I'm going to start off here. We'll write that we're trying to take the derivative of the larger y function. That's like my big f of x over there. So it's going to be a fraction, difference up above, something squared down below. So let's fill in the pieces. So we start off with just plain g of x. So I'm going to put in 4x to the power of 5 plus 2. And then we're multiplying that times the derivative of f of x. So that's that single term, 6x squared. The next term in the numerator, it's minus something. That something starts with the original f of x. So I'm going to write 2x cubed plus 5. And that multiplies times the derivative of g of x, which we calculated to be 20x to the power of 4. And then for my denominator, that is, again, the original g of x squared. So I'm going to write that 4x to the power of 5 plus 2, and that's going to be squared. So everything's been substituted in. From there, I just need to simplify. And this one involves a lot of distribution. So we'll begin in on the distribution in the numerator here. So I've got binomials times monomials. So I'll draw my little arrows to say what's distributing where. And we'll write our next step below here. So set up my fraction again. Set up my subtraction up in the numerator. So for my distribution of these left-hand pieces, 6x squared through 4x to the 5th plus 2. So the first multiplication is 4x to the 5th times 6x squared. That's going to give us 24x to the power. Add those powers to get new power of 7. Second distribution, 2 times 6x squared is going to be 12x squared. For the second set of distribution, I do need to put parentheses because of that minus sign. Then I can multiply 20x to the power of 4 times 2x cubed will be 40x to the power of 7. And then again, 20x to the power of 4 times 5 is 100x to the 4th. So I do see that when I simplify for my next step, I will be distributing that negative sign. We'll come back there because we need to distribute my denominator. So I see I've got in the denominator 4x to the power of 5 plus 2 squared. So over to the side, what I'll do is I'll write that as a separate expanded form so I can just see what that looks like. And then I do want to distribute it out. We'll write the polynomial in the denominator. So there's my double distribution arrows. So I first off have 4x to the 5th times 4x to the 5th. That's going to give me 16x to the power of 10. Then I've got 4x to the 5th times 2. For my outer terms, that's going to give a product of 8x to the power of 5. And that'll be the same as my inner product. Again, since I'm squaring the original binomial, it's also going to be 8x to the power of 5. And then my last term, 2 times 2, is going to be constant plus 4. So now I'm ready to distribute. And actually, what I'll do is I'm going to distribute in this step so that I can combine like terms in the next. So what I'll do is say this negative is going to go to both of these terms in blue, so they'll both become negative. And I can write that just by getting rid of the parentheses and then changing that plus on the 100 to a minus. And what that lets me do now is combine the like terms for the numerator. So I only got 2 like terms there. It's 24x to the power of 7 minus 40x to the power of 7. So that's going to be a negative 16x to the power of 7. And then descending order would put minus 100x to the power of 4 next. And then finally plus 12x squared. So there's my numerator. That's complete. And then for denominator, the two 8x to the power of 5 terms will add together. So that's going to be 16x to the power of 10 plus 16x to the power of 5 plus 4. And that completes it. So I'll put the derivative of y. And that is my final answer. Let's take a look at another example that involves a radical. So here I've got f of x equals 4 over the 4th root of x plus 5. So just like we did in a previous example, I want to start off by identifying what's my f of x, what's my g of x. So I see in my numerator I've got 4, so that's f of x. In the denominator I've got the 4th root of x plus 5, so that expression's my g of x. So let's set out our rule again so we can see what it says. Again, it's the derivative of big F of x is g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x, the original, squared. So I need to find my derivatives of these separated out f of x and g of x from my original. So that's going to be the derivative of 4. That's a constant, so that's going to be 0. The derivative of g of x is going to be really based on how I'm dealing with the 4th root of x. I'm going to call that here for the derivatives purposes x to the power of a quarter. Remember, that's equivalent to the 4th root of x plus 5. So the way that works now is as a simple power rule. Bring that quarter power down as a coefficient, and then I want to raise it to the power of 1/4 less 1. And then the derivative of 5 is 0. So for my simplified version here, it's going to be 1/4 x to the power of -3/4. Well, we're ready to plug in. So I'm going to pick up and write this derivative of f of x. So notice we'll set up again with the fraction, the subtraction, and the square. That's the overall structure of the quotient rule. And then I'm going to just fill in the parts. So remember, it starts with original g of x. So I'm going to write those with the rational exponent. So x to the power of a quarter plus 5 times the derivative of f of x. That's 0. So nothing much is going to come of that first product. That's in a way gone because of the 0. So it's all down to the second product, 4 times the derivative of g of x, which we calculated to be 1/4 x to the power of -3/4. And then for my denominator, that's the original g of x squared. So that's going to be x to the power of a quarter plus 5 squared. Just like with the previous example, I'm ready to simplify. So now I see that first term's going to cancel. So in my fraction, I'm going to multiply -4 times a quarter. So that's going to just reduce to -1, or just negative. And then all that's left from that other multiplication is x to the power of -3/4. For my denominator, I want to bring that x to the power of a quarter plus 5 and expand it. So it's that binomial times itself. And that we need to double distribute again. So I'm going to draw those arrows, first, outer, inner, last. And we'll write the product down here in the denominator. So x to the power of 1/4 times itself. Remember, you add up those powers. So it's going to be a quarter plus a quarter is a half. And then the outer term, x to the power of a quarter times 5, is going to be plus 5x to the power of 1/4. And the inner terms will be the same, 5 times x to the power of 1/4. And then the last terms will be 25. So now we want to simplify that fraction. I'm going to bump over here to the right. So I notice that this negative power that I have on x in my numerator, remember the negative power doesn't really make the base negative or that whole term negative. It moves it to the other side of the fraction. So if I see that x to the power of -3/4 in the numerator, it's the same as x to the power of +3/4 in denominator. So that's where I'm going to let it move, and its power becomes positive. The negative will persist above, and I'll just place a placeholder 1 there. And then I'm going to multiply all that in the denominator times that trinomial. So I want to combine those like terms. So this is going to be x to the power of a half plus 10x to the power of a quarter plus 25. So one last distribution, and this one is complete. I'm going to distribute that x to the power of 3/4 through. So what we'll have here is going to be -1 over x to the 3/4 times x to the power of half. Remember, I add up those powers. So half is 2/4. So this is going to be x to the power of 5/4. And then x to the power of 3/4 times 10x to the power of 1/4 is going to be 10x to the power 3/4 plus 1/4 is 1. And then lastly, plus 25x to the power of 3/4. And that is complete. I'll just identify that as the derivative of my original fraction f of x. Let's take a look at one last example that involves the natural exponential, e to the power of x. So here I've got the function f of x equals x squared plus 1. Let's just start by identifying that numerator is my little f of x. Again, not to be confused with the actual function itself, not the same thing. The denominator here is going to be x times e to the power of x, and that I can simply say is my g of x. So just to kind of follow up here, whatever is in the place of the numerator will be the little f of x, whatever's in the denominator will be little g of x. So remember that rule. I'm going to write it again just so you see it a third time. The derivative of big f of x is going to be g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. So just the same, we need to find the derivative of these two numerator and denominator. So the derivative of f of x, little f of x. If the original is x squared plus 1, the derivative will be applying the simple power rule. 2, the old power is a coefficient, x to the power of 2 minus 1, plus the derivative of 1 is 0. So that would simplify as simply 2x. The derivative of g of x is slightly different because the original is a product. So what we need to remember is, how do we deal with a derivative of a product? So although we are taking the derivative of a quotient, what we have here within this quotient is another product. So I need to apply the product rule. So within all this, what I need to identify is that, hey, this x, let's just give it another name here. This is going to be my, we'll call it h of x. So h of x is x. So let's identify then the e of x here. Let me choose another color so we keep stuff distinct. Let's call that j of x. So here's a good time to review the product rule. So the product rule, if I've got, let's say, big H of x, and we're not taking derivative yet. So big H of x, if that's the product of little h of x times little j of x, the derivative is going to be h of x times the derivative of j plus j of x times the derivative of h of x. So it kind of shares a similar structure with my quotient rule, to have them side by side here, with the difference that this one is just one level and it's addition in the middle. So to take this derivative of my denominator, which is a product, let me find the derivative of its parts. So the derivative of h of x, which is the derivative of x, is going to be 1. And then the derivative of j of x, that unique function e to the power of x, is its own derivative. So remember, derivative of e of x is e to the power of x. So all I got to do is fill in here to get my derivative of g of x. So I'm going to fill in my rule here. So it's going to be x, that's the original h of x, times the derivative of j of x, which is e to the power of x, plus the original function j of x, which is e to the power of x, times the derivative of h of x, which is 1. So the way that derivative of g of x will look is x times e to the power of x plus e to the power of x. So we did have to take a side step there because one of my functions, the one in the denominator, was itself a product. Well, let's put the parts together. So now I want to work on taking the derivative of the whole fraction, which is this original f of x. Set up my numerator, and remember it's a minus up there, and down below it's a square. So let's fill in the parts. And again, it helps to label stuff because that way you don't have to go farther than just saying what's my label. So g of x here is that original, x times e to the power of x. And then the derivative of f of x is 2x. The original f of x is going to be x squared plus 1. And then times the derivative of g of x, that's the one we had to create with the product rule, is x times e to the power of x plus e to the power of x. And that's all over g of x squared. And that's going to be x times e to the power of x squared. So now we're ready to simplify. Let's combine some of these products. So we'll create our fraction again. So for my first product, it's really going to be a monomial because it's a monomial times a monomial. So x times e to the power of x times 2x is going to be 2x squared e to the power of x. Okay, now we've got a binomial. So it's x squared plus 1 times x e to the x plus e to the x. So I'm going to draw my distribution arrows there. So x squared, the first term, times x e to the power of x is going to be x to the power of 3 e to the power of x. Outer term, x squared times e to the power of x, just itself. X squared e to the power of x. Inner term is going to be 1 times x e to the power of x. So it's just, notice the x's are going down by powers. And then lastly, 1 times e to the power of x is just e to the power of x. And that's all over this squared term. So that, again, I don't need to FOIL because it's just a monomial that's squared. But I will note that that square applies to both of the factors in the monomial. So x e to the x all squared is going to be x squared times e to the power of 2x. So now we're ready to combine like terms there in my numerator. So what I'll notice here, and I'll make this shift right now in the actual question, is that this negative sign needs to distribute to each of these 4 terms. But the kind of the outcome of that distribution is that each term will become negative. So I'm going to take off the parentheses, make each term negative, and that completes the distribution. So now I just need to check and see, do I have any like terms? I notice that most of those terms were descending power of x's, but I do have two that are identical in terms of their powers set up. So 2x squared e to the x will match with negative x squared e to the x. So that I need to combine. So in my final answer down here, I'm going to write 2x squared e to the x minus, I can think that that is 1 x squared e to the power of x is going to just be 1 x squared e to the power of x. And then the other terms I'm just going to write in. I probably should put the minus x cubed first because it's the highest power of x. So what I'll do is I'll make some space here in the numerator. Negative x cubed e to the power of x plus the 1. And then the other pieces I can just write in. So it's going to be minus x to the power of 1 e to the power of x minus e to the power of x, all over x squared times e to the power of 2x. So at that point, what we need to see is that I've got something that I could cancel from each one of these. I could cancel from each one of these terms. And what I want to just do is highlight what's the same. So it looks like I got an e to the power of x here in each term in the numerator. And then I also have e to the power of 2x in the denominator. So those are going to represent a cancellation. So all I need to do is apply my quotient rule for powers for combining. And remember, if I have that situation, I subtract to decide how the powers resolve. So what I do know is that all these e to the power of x's in the numerator will cancel. What I need to decide is what's going to cancel from this lower e to the power of 2x. Well, if I just take the two powers, and what I'll do is I'll set up my denominator first for this final answer. So it's going to be x squared times e to the power of 2x minus the x that's represented in each one of those powers above. And then I can see there, okay, 2x minus x, what's that going to leave me with? 1x, or just simply x. So that represents after the cancellation. So what I can write in my numerators now are these four terms without the e to the power of x. So it's negative x cubed plus x squared minus x minus 1. And that is a final simplified answer. Thank you for joining for this investigation of the quotient rule for derivatives. I'm going to let you differentiate your own quotients. See you soon.